Okay, so we're going to talk about in this chapter energy, which is also sometimes the first law of thermodynamics, the conservation of energy. Then afterwards, we will go forward to, I want to say 16 maybe or 17, and that will then be kind of the rest of thermodynamics. We'll talk about entropy, gives free energy as well. Let's talk a little bit about energy. When we talk about sort of energy, a lot of times we're talking about really the flow of energy or heat. And when we talk about sort of that exchange of energy, it really involves really kind of two parts. One is what is referred to as the system. The system is pretty much whatever you're interested in. So if you're doing an experiment in a test tube, your system would be the test tube. If you did it in the beaker, it would be the beaker. And then pretty much everything outside of your system is considered the universe. And a lot of times what we'll talk about here is, especially in this chapter, is that flow of energy from one place to the next, either from the system to the surroundings or vice versa, from the surroundings back into the system. There's kind of three types of systems that we sometimes come across. One is an open system, and in an open system, there's exchange of both mass and energy with the surroundings. Like an open beaker, you can reach in and pull stuff out, and there also can be the exchange of energy that happens. A closed system, we do have transfer of energy, but mass basically remains the same. And in an isolated system, there's no transfer of mass or energy in those systems. There's some pictures of that. Again, an open system, you could take stuff, mass in and out. We also have that heat flow. Putting a stopper, for example, on top of your flask there will prevent, obviously, you from taking stuff out, but we could still have the transfer of heat and energy. And an isolated system, pretty much everything kind of stays inside there, no transfer of heat or energy or the mass. When we talk about energy, energy is really the capacity to do work or to produce change. Energy is equal to work done, which is force times distance. There's all kinds of different sort of energy that we come across. There's chemical energy, and that's energy that's stored within the structural units of chemical substances. For example, when we make and break bonds, there's energy associated with that process. In a chemical reaction, pretty much all that happens is we break all the bonds and they reform on the other side. So when we actually want to break a bond, we do have to put energy in to do so. And when that bond gains energy, everybody starts moving away from each other. They have enough energy basically to break apart from each other. And one of the things that we'll talk a lot about in the chapter is that idea of something that absorbs energy. That is what is referred to as an endothermic process. And that's opposite of when we want to kind of make a bond here. Basically, we need to remove energy. So if you have two things that want to come together to make a bond, as they lose energy, they really sort of lose the ability to escape one another, and they're able to make that bond. And when somebody releases energy, that is, as we will see, what is referred to as an exothermic process. There's also things like potential energy, and that is energy due to the position of an object. The classic example, right, is like the giant boulder on the cliff there that's about ready to fall off. That boulder has a certain amount of energy due to its position, and that is potential energy. Kinetic energy is the energy associated with the process there due to motion. And basically, if it should tip over here, it is now going to pick up some kinetic energy as it is falling down the hill. One thing that we think about when we deal with energy is what is sometimes referred to as the first law of thermodynamics, which is the law of conservation of energy. Energy is neither created nor destroyed, but it can be transformed from one form to another. we think of sort of the transfer of energy as being sort of perfect, if you will. So what that means is if somebody gives off a certain amount of energy, somebody else will basically absorb the exact same amount of energy. So there's almost like this perfect exchange of energy. And that's what we see here. Our boulder coming down the hill, right, picks up some kinetic energy. Eventually, it lands. Hopefully there's nobody there at that point. It transfers all that energy right to the ground or whoever's underneath it at that point. And it comes to rest at a different potential energy than it started with, right? All the energy in that process went somewhere, either to the rock, to the ground, or the person that was standing underneath that rock when it fell on it. They all pick up some of that energy that was transferred. Now, thermodynamics, as I mentioned, is really the study of heat and other kinds of energy. And as we'll talk about in a later chapter, we look at the second law of thermodynamics a lot to help us sort of understand whether or not a reaction will sort of be spontaneous or not, basically occur. Now, state functions are properties that basically are determined really by two things. Pretty much where you start and where you finish are really the two most important things when you're dealing with anything that is a state function. Energy, pressure, volume, temperature, these are all state functions. And that's why we always sort of do the change in energy is final state minus initial, change in pressure, final minus initial, change in volume, final minus initial, and change in temperature, final minus initial. So it doesn't really matter how you get there. It just matters pretty much where you started and where you ended in terms of, for example, energy. And that's what we see here in this picture. Both hikers started over here. The blue guy here kind of took the more direct route up the hill. The red one kind of took the scenic route around the hill, but they both pretty much ended up there at the top, and they both ended up with the same potential energy. It doesn't really matter the path that they chose to get there. As we'll talk about in this chapter, and as you probably know as well, not all reactions basically occur in sort of a one-step process. A overall reaction could be a result of many individual sort of processes that occur, like, if you had A plus B goes to C plus D, then C plus D goes to E plus F. I'm just practicing my alphabet here. And if we add these together, we could cross out whatever's on opposite sides of the arrow, gives us this overall reaction of A plus B goes to E plus F. Now, in terms of the energy for that final reaction, as we'll talk about, it is really just the sum of each of the individual sort of steps along the way. Speaking of reactions, when we think about, this idea of kind of final minus initial, when we think about an actual reaction that we're dealing with, we have reactants on the left-hand side of the arrow going to our products. And pretty much our products are our final state and our reactants are our initial state here in a reaction. So a lot of times, especially as we'll talk about a little bit later on, we talk about delta H, which is the enthalpy, a very common way that we sort of calculate something like the change in energy for a reaction is to take all the energy of our products, which is pretty much where everybody ended up, minus all the energy of our reactants, where everybody pretty much started. So that's kind of the final minus the initial as well. Any questions on that? So energy, there's some different types of units that we typically come across. So let's talk a little bit about that here. The SI unit, which is the standard unit, is a Newton meter, although in chemistry, we really don't use that all that much. We do use, this occasionally does pop up, and that is a kilogram times meter squared over second squared. Very common unit of energy are joules, so that's not negative, that's just from PowerPoint. And 1 joule is equal to a kilogram meter squared second squared. And from first semester, you might have seen that happen in a couple of equations. Kilogram over a meter squared second squared is basically a joule. And also very common units of energy is kilojoules. So 1 kilojoule is 1,000 joules. Other common units that we sometimes use for energy are calories. And a calorie with a lowercase c is the amount of energy required to raise 1 gram of water by 1 degree Celsius. And the relationship between calories and joules, get rid of that as well. 1 calorie is 4.184 joules. And that's a conversion that's sometimes used. Kilocalories is also another common unit of energy. 1 kilocalorie is 1,000 of the little calories. And why I say little calories in terms of C's, because there is also a capital calorie, which is a nutritional calorie. So if you see a capital C, that's a nutritional calorie. 1 calorie like that is actually equal to 1,000 of the little calories. And that's equal to 1 kilocalorie. So if you're talking about nutrition or something like that, or either those calories you see on your packages of food, the energy associated with that food is more of a nutritional calorie, which is 1,000 of those little guys. One way that we use energy is to change the temperature of a substance. Obviously, if we supply energy, for example, to ice, which is the solid version, right, of water, it will absorb all that energy. And that's what happens really when you take an ice cube out of, say, the freezer, even though you don't really maybe even do anything to it, the outside, right, is hotter, right, than the ice cube there. So energy always flows from, or heat always flows from hot to cold, right? So when you take it out, that ice cube is going to pick up all that heat and energy from the air, right, that's in the outside of the freezer, and it will start the melting process. Now, thermal energy is a little bit different than temperature. Thermal energy is the energy associated with the random motion of atoms and molecules. The amount of thermal energy that you have is related to the amount of molecules or atoms that there may be in a particular substance. The more atoms, the more molecules that you have, there's going to be a lot more molecular motion happening and a lot more thermal energy. And again, it is slightly different thermal energy than temperature. We use temperature to represent sort of, how much energy is sort of happening in that particular area. So just to sort of illustrate the difference, if we had a cup of coffee at 70 degrees Celsius, has a higher temperature than, say, a bathtub of water at 40 degrees Celsius. But in terms of thermal energy, the bathtub would have much more thermal energy because obviously in the bathtub, there is a lot more water molecules, right, than in the coffee cup. So a lot more water molecules in that bathtub will result in a greater thermal energy than you would see in the coffee cup. Even though the coffee cup has a higher temperature, because it's a much smaller volume, right? So you don't need as much energy there to see a bigger change in the temperature as you do obviously in like the big bathtub. You could think of it like, right, if you heat it up like a cup of water, right, it probably would heat a lot faster if you heat it up to a big pot of water, right? It takes a little bit longer to get the temperature up and going because there's a lot more molecules. So there is a difference again between thermal energy and temperature, although we do use temperature to sort of help us understand what's happening in terms of energy, who's absorbing energy, who's losing energy. Typically, somebody absorbs energy. We usually can see that reflected in temperature because temperature goes up, right? And if somebody gives off energy, we usually can see that as representative as the temperature will go down in that particular substance. Heat, as I mentioned, is that difference in that flow of energy between two bodies that are really at different temperatures. And as I mentioned before, it always sort of flows from hotter temperature to colder temperature. So the guy that's colder will sort of warm up, if you will, and the guy that's hotter will kind of cool down. If you have them, as we'll see in the picture in just a second, sort of an insulated container, they probably will meet somewhere halfway between their temperatures. If you average out the temperatures, they'll probably end up somewhere in that ballpark. As we talked about a lot here, exothermic processes versus endothermic processes. Anything that is an exothermic process, again, is always a process that basically releases heat or energy, transfers it, for example, to the surroundings. If you strike a match or something like that, light a Bunsen burner, obviously you can feel the heat and energy coming off from the flame, and those are exothermic type processes. Endothermic processes, again, are opposite of that. That is basically when energy is being absorbed. when we think about energy and we do calculations, as we'll talk about obviously in this chapter, there is sort of a representation in terms of exothermic and endothermic in terms of the values that you typically get for numbers. And as we will typically see, exothermic processes usually end up with a negative value for their energy, be that the enthalpy or just the actual heat or energy that you calculate. It's usually a negative value, and that represents that that process is going to be exothermic. Opposite of that is endothermic is usually represented by positive sort of values when you calculate them. So if you see an energy value that's positive, in most cases, you could assume that that's going to be more of a endothermic type process. And we'll do some calculations a little bit later on in this chapter. And it is important when you do sort of quote energy, if you will, that you do keep either the negative there if it's supposed to be there, or if it's positive, obviously you keep it positive. Again, it gives a person that looks at that value an understanding of sort of what's happening in that process. Is energy being absorbed or basically given off? So these are two energy diagrams, and energy diagrams do represent sort of what is happening also in terms of a reaction. So if we look at this here, the energy diagram on the left is an exothermic diagram. We have energy and we have the progress of the reaction that's happening here. And we have our reactants right about here. So these are our reactants. And down here are our products. And what we see in this diagram is our reactants are starting higher in energy than our products, which means the only way for basically those guys to get down to where the products end up is overall the energy here has to be released, which is why it is sort of a exothermic process. Right-hand side energy diagram here, we have our reactants and our products here. And in this case, our reactants are actually lower in energy than our products. So in order for sort of our reactants to get to the product side in terms of energy, the opposite is true here. Energy has to be absorbed in this case. So another really important part of this diagram is this hill. And it's sometimes referred to as the hill that the reactants have to climb. And this is what is known as the activation energy. And the activation energy is sometimes abbreviated E of A for activation energy. And that really is the minimum amount of energy needed for a reaction to occur. So when a reaction takes place, there's really sort of two things that has to happen. There has to be some type of collision between the reactant molecules, so they have to collide, and they really do have to collide with the right amount of energy to sort of kick off that reaction, which is the activation energy. Not all collisions do end up in products being formed, so just because a couple of reactants bang into each other and collide with each other, it doesn't necessarily mean that the products will be formed in that case. You have to have the right amount of energy. And the other important thing is you actually have to hit each other sort of in the active side of both of those things for the right sort of reaction to sort of take place. So just a collision doesn't always necessarily mean that a reaction in products would actually happen. So what happens in a reaction, as you should hopefully know, right, is all we are doing is taking all of our reactants basically and breaking apart all those bonds. And then they're basically reassembling right on the product side as new substances. So what happens in this journey of reactants heading to the products is as they start moving up this hill, they're really starting to break bonds. And they're actually starting to make bonds as well. So as they sort of progress up the hill, you have some bonds starting to break, and you have some bonds that are starting to make till they get really to the peak of the hill right about here. And that is what is referred to as the transition state. Now, the transition state, you will also find up there what is sometimes referred to as two things. Sometimes referred to as a transition state complex, are sometimes referred to as an activated complex. And this sort of guy that's sort of right here at the very top, I'm just going to put an X right there at the very top. It is pretty much at the peak of energy. And in chemistry, right, things with high energy, is that usually a stable situation or not so stable? Do things want to be really high in energy? They do not. Really, the goal, pretty much everything in chemistry is to minimize the energy, which creates a much stabler sort of situation. So the goal here is to have stable situation, lowest energy possible. So the transition state there in our diagram is pretty much the peak of energy that you could have. And that transition state complex is pretty much unstable in that sense. And because what you actually have at that point is something that has partially made bonds and partially broken bonds. So it is, as the name implies, really the transition state complex is kind of partially broken all those bonds that it needs to break, and it's really working on making all the new bonds as it goes there to the products. So usually relatively quickly, this guy will kind of drop down the hill to the product side. That's why it's very hard sometimes to try to isolate that transition state complex, because it really doesn't hang around a very long time. It's very high in energy, which is not good for stability. And it has those partially made bonds, partially broken bonds. And it usually will try to drop down to their side very quickly. Any questions on that there? We also see here on our endothermic process, this would be our activation energy here. Which one has the larger activation energy? It is the endothermic process, right? The one on the right there has the bigger hill to climb. That activation energy is also plays a really key role in the kinetics of the reaction. If you have a much larger hill to climb to get to the other side, reaction going to be faster, slower? Yeah, it's going to be slower, right? It's got a big hill to get up to the other side. You might not have a great proportion of molecules that have enough energy basically to get up and over to the other side, as opposed to a much smaller activation energy hill. You'll have a greater proportion of reactants that have enough energy to get up and over to the other side, and you typically will see the reaction sort of occur faster. Now, in terms of energy, one very common way that we calculate the energy is, as we'll see here, what is referred to as delta H. Delta H is the enthalpy of a reaction. It is basically the heat of a reaction. And on this diagram, since we're looking at it, to find really the delta H of a reaction, you basically take the difference in energy of your products minus your reactants. So for this one here, that is this guy and this guy. And that energy difference between these two is our delta H. And if we look just at the position of each of those, products here are lower in energy than our reactants. That means when I take my products minus my reactants here, I have a smaller number minus a larger number, which will end up with a negative value typically. And again, that's why exothermic is usually a negative value for energy, and delta H for sure. If you see a delta H value that's negative, it is exothermic. If we look at our endothermic reaction here, that is our reactants, that is our products. And if we take the difference between the energy of those two, that is our delta H. And in this case, for endothermic, we can see that our products are actually higher in energy than our reactants. So when we do our product minus our reactants, we have a larger number minus a smaller number will result in a positive value for delta H in this case. And that is why endothermic reactions are usually positive in value. And delta H, as we talked about, I think when we did Le Chatelier's principle, is typically the very common way that we kind of represent energy for reactions. Any questions on any of that there? And that's what we see here, exothermic. This is basically the formation of water. Reactants higher in energy than products, going to have to give off that energy to the surroundings. Vice versa here, decomposition of mercury 2 oxide needs energy to go in to do that, to heat it up a little bit, absorbs the energy, and will make our products, which end up being actually higher in energy. So as we sort of alluded to here from our conversation, exothermic reactions and what we talked about when we were talking about Le Chatelier's principle, although maybe not correct in all aspects of it, we think of heat and energy as being more of a product in an exothermic reaction. It is like it's being given off. So sometimes you may even see heat written on the product side or an actual value like we see here, but definitely our delta H here would be a negative number. It really doesn't matter the value for delta H, where it only matters in terms of exothermic and endothermic is actually the sign. So as soon as you see that negative sign on the energy value, you know that it is an exothermic type process happening. Opposite of that is a endothermic process, as we talked about when we did Le Chatelier's principle. Endothermic is considered more of a reactant, like it's being absorbed in that reaction. And that's why we will oftentimes see it on the reactant side. And once again, our delta H guy will be a positive value here in that type of process. All right, so this is sort of what we're talking about. We have two sort of waters here at opposite temperatures in this isolated insulated container. Again, energy is going to flow from the left to the right there. That's going to increase the energy of those water molecules there on the colder side. Also going to decrease the energy of those guys on the hotter side, right? Because they're losing that energy, so they're going to slow down. The result of that is we're going to see their temperature come down. And on the cold side, we would see the temperature come up. And again, as I mentioned, they'll probably meet somewhere in the middle if you have a nice insulated container such as this. So we talked about enthalpy here, but let's officially talk about enthalpy. That was a good talk. So most reactions are carried out under constant pressure conditions. So when you do reactions in the laboratory, you really don't monkey around with the pressure all that much, or even really the temperature in a lot of cases. So a lot of times those things are constant, but definitely when you do a constant pressure sort of situation, you could very easily calculate the enthalpy of a reaction, which we'll do in a later experiment by just really following the temperature change that occurs with a thermometer and maybe some type of water. So the enthalpy is used to express the heat of energy that's either released or absorbed. And the delta H is what is referred to as the change in enthalpy. And as I mentioned before, the common way that we do it is, again, really our final minus our initial state. So we take the delta H of the products minus the delta H of the reactants. Again, that's really our final minus our initial. So really you add up all the delta H values for the product side, and you add up all the delta H values from the reactant side, and you basically subtract them. Typically, delta H, or the change in enthalpy, the units are typically kilojoules. Kilojoules per mole usually is the common units that you associate there. One really important thing, for example, is if we had a reaction like 2A plus B goes to 3C, you can find the delta H values, sometimes referred to as the delta H of formation values, in tables. So you can find it in a thermodynamic table in your book. And if you look up those values, for example, we'll just say A is minus 136 kilojoules, clearly just making these numbers up. B is plus 26 kilojoules, and we'll go with C is minus 45 kilojoules. So you would look up these values, and a couple important things if you go to a thermodynamic table to look up the values of, say, delta H, later delta S or delta G that we will do in a later chapter. You want to make sure you look up it correctly, and what I mean by that is you want to make sure you find the substance, but you also want to make sure you find the substance in the correct state. So if it's a gas, you want to make sure you get the value for the gas. If it's aqueous, you want to make sure you get the aqueous value, and so forth. So there will be different values depending on the states of those substances that you look up, and you want to make sure that you get the actual correct ones. So if we were to calculate this delta H for this reaction, we would take the delta H value of all of our products, and then we would subtract it from the delta H value of all of our reactants. And there is an important thing. We do need to take the actual coefficients into account when we do this calculation. So if we were to calculate this and we went to the table to find these values, we would start with our delta H here is equal to our products, which is C. We would take 3 times the value of C from the table, which would be 45 kilojoules. And that is all of our products. And again, the 3 comes from the coefficient, because technically speaking, when you do look it up here in the table, it actually is kilojoules per mole is typically the values that you would see. So we're basically multiplying by the number of moles that we have, which is the coefficient. So that is where all those numbers come from. We then would subtract it from our reactant. So on the reactant side, we have 2 of A. So we take 2 times the value of A from the table. Plus we have 1 of B. So basically 1 times the value of B from the table. And then we will add it up, as I just made this up. Let's see what we did. We end up with 3 times minus 45 minus here 2 times negative 136 plus 26. Looks like if I had it up right here, we get 111 kilojoules in this case. That would tell us in this made up reaction, this is exothermic or endothermic. This would be endothermic, as it is a positive value that we ended up with. So you basically take the products minus the reactants. You got to also, again, make sure that you take into account the coefficients that you see there. I will say that when you look up in a delta H table, there are certain things that basically have a delta H value of 0. And those things that have delta H values of 0 in the table are things in their standard state that are not combined with anything. So kind of like elements by themselves. So if you had like sodium metal, it would probably have a value of 0. If you have something like oxygen gas, O2 or something like that, it would have a value of 0. So a lot of elements in sort of their natural state that's not combined with anything else have delta H values basically of 0 in the table when you look at them up. Any questions on how to calculate that? All right, let's try some here. I think I inserted some that you don't have, so I apologize, but give it a go. All right, with this reaction here, calculate the delta H of this reaction and also determine is it exothermic or endothermic. Okay, let's take a look. So once again, if it wasn't provided for you, you would have to hit a delta H table. Usually found, like I said, in the back of your textbook, usually has them. We're going to calculate the delta H here. And again, for this reaction will be our delta H of our products minus the delta H of our reactants. Once again, we do want to take the coefficients into account. So our delta H of this reaction would be 2 times the value of sodium hydroxide, which is minus 470 kilojoules per mole, plus basically 0 here for H2 kilojoules. That takes care of all of our products. We'll do the exact same thing for our reactants. We have 2 of our sodiums, which is basically 0 kilojoules as well, plus 2 of our waters, which is minus 286 kilojoules, obviously per mole. And that takes care of all of our reactants. And in this case, basically, we're just taking 2 times minus 470 minus 2 times minus 286. Gives us a delta H in this case of minus 368 kilojoules. That means this reaction is exothermic or endothermic. It is exothermic, as we do have a negative value here. Yeah. Any questions on that calculation? All right, let's try another one here. I think I threw a couple of these in here. Maybe. Let's go to this one. I think. Yeah, let's see this one. That looks good. All right, calculate delta H of this one, and also again, exothermic or endothermic. Okay, let's take a look one more time here. So again, these are table values. Obviously, they're sometimes not provided for you, so you have to look them up. And once again, the delta H of F means delta H of formation, which is typically the values that you find in those tables. So we're going to do our same thing here. We're going to take our products. So in this case, making sure we also take into account our coefficients. We're going to take 12 times the value of CO2 from the table, minus 393.5. We're going to add it to our other product there, which is 6 times the value of water from the table. And that will then take care of all of our products. We will then subtract pretty much the same deal for our reactants. So we got 2 times our C6H6, which looks like 4904. And we got 15 times a whopping 0 kilojoules, which again, most things in their standard state have a value of 0. And that is going to take care of all of our reactants in this case. So looks like 12 times minus 393.5 plus 6 times minus 286. Going to take that and then subtract 2 times 4904. Looks like a winner. And it looks like we end up here negative 6536 kilojoules. Once again here, we got a negative value for our delta H value, which means that this would be exothermic. Yeah. Any questions on how to calculate delta H's here from the thing? Pretty much if you're asked to calculate delta H of a reaction and the only thing given to you is the equation, go to the table, find the values, do products minus reactants is really the right way that you would want to calculate. Any questions? Okay. Another sort of relationship for delta H here is we can actually use our energy value if it's given to us in a reaction and the equation and really come up with conversion factors to help us do certain types of calculations. And those conversion factors are pretty much like stoichiometry. So first off here, we have this reaction and it has a delta H value of negative 2221. That tells us that this reaction is exothermic because it's negative. From this reaction, we can have a lot of relationships that are much like we do with stoichiometry, but related to the energy. We could say for every 1 mole of C3H8, that's what it says. We get out basically minus 2221 kilojoules. We could say for every 5 moles of O2 we put in there, we get out minus 22.1 kilojoules. For every 3 moles of CO2 that we form, we also get 22.1 kilojoules. And lastly, for every 4 moles of water, we get out the same amount of energy, right? So we could use this almost like we do with stoichiometry. Instead of like a mole to mole relationship, we could kind of do a mole to energy relationship. And just like stoichiometry, for each of these equalities, you could really write 2 conversion factors. For example, you could write 1 mole of C3H8 over minus 2221 kilojoules. Or you could flip it around and use that energy up on top over 1 mole of C3H8. So when we have a question like what we have in this problem, which is assume that all the heat comes from the combustion of propane, which is the C3H8, calculate the delta H when 0.113 moles of propane is burned in excess oxygen. So basically we have our moles here of propane, and we really want to know how much energy we would get. So we would go to the equation and find really, again, like stoichiometry, kind of the mole to energy relationship. And again, that gives us our 2 conversion factors, which we could use in this case, the guy on the right, because that will cancel out the moles. And that will put our energy up there on top. And that will give us that there is minus 2221 times 0.113, about minus 251 kilojoules of energy is going to take place. So we could use this kind of like stoichiometry, mole to energy relationship. Obviously, variations of this is they maybe don't give you moles, but they give you grams of propane, convert grams to moles, very much like stoichiometry type steps, and then do kind of the mole to energy relationship that you get from the equation. Any questions on that? These are sometimes referred to as thermochemical relationships because it involves the energy and sort of the mole-to-mole relationship. Any questions on that version there? And clearly we could do it for anybody else in the equation if we were interested in oxygen or how much CO2 and so forth. Okay, the next sort of thing we're going to talk about in terms of energy is what is referred to as specific heat. And let us talk about that then. Specific heat or specific heat capacity is the amount of energy that's required to change 1 gram of a substance by 1 degree Celsius. It's pretty much the same definition as the calorie, which is the energy required to change 1 gram of water by 1 degree Celsius, but this is any substance. There is a formula for specific heat capacity, and it is Q is equal to ms delta T. Q is heat or energy. Typically has units of joules or calories is typically the units. M is mass, which typically has units of grams. S here is the specific heat capacity, which is that definition we just talked about. And it has units of either joules per gram per degree Celsius or calories per gram per degree Celsius. And here, T is actually the change in temperature, which is always final minus initial. You definitely always want to do final minus initial here because frankly, that is what's going to tell you whether or not your reaction is going to be exothermic or endothermic. The specific heat capacity is a positive number, mass is a positive number, so really it's just the change in temperature that will determine whether or not this reaction will be sort of exothermic or endothermic. By the way, this is one of the few things in chemistry where degrees Celsius, you can leave the temperature in degrees Celsius. And that is because in most cases in chemistry, the specific heat capacity is given in degrees Celsius. So you're usually okay in that unit. I know in physics, sometimes they use Kelvin, but here in chemistry, we oftentimes will use degrees Celsius with our specific heat capacity. The specific heat of liquid water, I'll get rid of that, is again, that's not negative, that was just from PowerPoint. So specific heat of liquid water is 4.184 joules per gram per degree Celsius. Or if you're doing the calories version, 1 calorie per gram per degree Celsius. That is a useful number that comes up a lot because we kind of always assume a lot of things are kind of water-based. When we have aqueous solutions, it's basically water-based. So a lot of times we use the specific heat of water, one of those two numbers. That is also, by the way, as we saw earlier, the conversion between a calorie and a joule is basically that number, right? 1 calorie is 4.184 joules. Now, sometimes specific heat capacity will not be abbreviated as an S. Some people will use SH. Some people will use C, whatever you like. I go with S, but you can use either of those things as well. If we calculate Q, which is heat or energy, it kind of works the same way as everything else. If you calculate a Q and it is a negative value, that is an exothermic process. If you calculate Q and it is a positive value, that is an endothermic process. And if you do an experiment like this, a specific heat experiment, it is a pretty simple experiment because frankly, all you have to do, you could take a couple of insulated cups, you could do your reaction in the cup, you could throw a thermometer in there, and basically by just simply following the change in temperature that occurs with, say, water, you can figure out how much energy was either absorbed by the water, you can figure out how much energy was released by the water if you're doing sort of the opposite. So it's a very simple sort of process. And if you do that sort of reaction under constant pressure, the Q value will equal the delta H value for that reaction. So they will basically be the same thing if you do it under constant pressure conditions. If it is a exothermic process, my final temperature will be, it will be the change in temperature, right, will end up being a negative value, right, which means that my final temperature will be lower than my initial temperature, right? It gave off all that energy. The result of that is the temperature of that substance will come down. If it's endothermic, that change in temperature part is important because my final temperature will be higher than my initial temperature. Basically, that substance gained all that energy. The result of that is we see the temperature go up, right? So the final temperature will be higher than the initial temperature. And that's why it's really always important to do final minus initial. Sometimes people are taught this in a lower level class and they go, just take the difference of the temperature, right? It doesn't really matter. So again, that is the part that's really going to determine whether or not it's exothermic or endothermic. So make sure you always do negative or final minus initial. So this is some specific heat capacity, and it's also important when you look it up in the table that you look at the state, especially with water. Liquid water is 4.184, but you can see ice and steam, which is also water, has a specific heat capacity more of 2, right, rather than 4. If I have a really high specific heat capacity, does it take more or less energy to change the temperature of that substance? It takes more energy, right? Because specific heat capacity is joules per gram per degree Celsius, amount of energy needed to raise 1 gram by 1 degree Celsius is basically what the definition means. Water has a really high specific heat capacity, right? Which is why people freak out when the water temperature goes up just a little bit, right? Because that's a lot of water and that's a lot of energy to make the water go up, just that little bit of temperature, right? That's why, you know, people are concerned about that. Obviously, if you have something with a much smaller specific heat capacity, it takes less energy, right, to move the temperature of that substance. All right, let's try one here. Determine the amount of energy as heat that's required to raise the temperature of 10 grams of a substance of aluminum from 20. So we're going to use our specific heat equation, Q equals ms delta T. In this case, we have the mass, which is 10 grams. We have the specific heat capacity, 0.89 joules per gram per degree Celsius. We got an initial temperature there of 25 degrees Celsius and a final of 58 degrees Celsius. So we pretty much got everything we need just to plug it in. That gives us 10 grams times our specific heat capacity. And we're going to take, again, our final, which is 58, minus our initial temperature here. Grams will cancel, degrees Celsius will cancel. That will leave us joules as our answer. And we will get like 293.7 joules. If you're still into that whole sig fig thing, right? That's like a 290 joules, I suppose, if you want to do that along in that case. Any questions on that there? We also want to convert this into calories. So again, 1 calorie is 4.184 joules. We'll use our rounded number there, 290 joules. And we got 4.184 joules on the bottom is a calorie. The joules will cancel. And in this case here, she used a rounded number on my calculator, 4.184. Looks like perhaps a 69 calories in this case. This would be a endothermic process, right? Because we got a positive value there for Q. We also see that as well, right, that the temperature increased from its initial to final, and that's a result of it gaining energy, right? So as it gained energy, the temperature reflected that and it went up. Any questions on that there? All right, let's try another one here. 294 joules of heat is transferred to 10 grams of silver. What is the final temperature of silver if the specific heat capacity is 0.24 joules per gram. So once again, here we're going to use our equation, ms delta T. We do have Q given to us at 294 joules. We have our mass, which is 10 grams. We have our initial temperature here at 25 degrees, and we're looking for our final temperature. And we do have the specific heat capacity given to us at 0.24 joules per gram per degree Celsius. So however you want to do it, you can plug everybody in if you like. So that's going to give us a 294 joules. It's equal to our mass, which is 10 grams, times our specific heat capacity of 0.24 joules per gram per degree Celsius. That's going to be times our final temperature, which is what we're looking for, minus our initial, which is 25 in this case. Mathematically speaking, we probably want to do it correctly. So we got to like do some division of those guys, right, to the other side first before maybe we tackle anything inside. Or you can multiply them together and then multiply inside and then do it that way, however you want to do it. So I'm going to divide both of those guys to the other side just to kind of clean it up a little bit. That's going to be 294 divided by 10 and divided by a 0.24. Going to give me about a 122.5. By the way, when I do all that, joules here will go away, grams will go away, and that's going to be degrees Celsius when I do that. And that would equal our final temperature minus 25 degrees Celsius. At this point, I then should add this, right, to the other side. So I'm going to add 122.5 plus a 25, and at that point there, we will end up with like a 148, we'll call it degrees Celsius in this case. Final temperature went up. Now, if you did a lot of strict sig figs and you took this guy to 2 sig figs, you would get a $1.20 plus the 25 would get you a 145 on the final temperature there if you did a little early rounding, which is okay as well. Any questions on that there? All right, I think we'll lay it up there for today.